In this video, we're going to look at a particular example of a directional alternative t-test. Blood cholesterol levels are compared in randomly selected people from Humboldt County, some of whom have recently experienced a heart attack, and the others did not have a heart attack recently. Those served as a control group. Do people who have recently suffered a heart attack have significantly higher average cholesterol levels than people who did not recently suffer from a heart attack? So we have the two samples and their summary statistics here, and based on some prior knowledge, we might anticipate that individuals who have higher cholesterol would be at a higher risk for cardiac arrest. The hypothesis of will a particular group have a larger average than another group is justified. Before we begin to crunch numbers, our first step is to verify that the assumptions of the t-test are met. The samples must be randomly and independently selected. Let's see. In the description of the study, we are told that the subjects were randomly selected, so that's good. And there wasn't any pairing going on. Right? The people who were chosen in the heart attack group did not determine the individuals who were chosen for the control group, or vice versa. Secondly, the observations must be considered independent. I think that's a fair assumption that any one individual, regardless of the group they're in, my cholesterol level is probably not influencing or dependent upon another individual's cholesterol level. Lastly, the requirement that often takes a little bit of work is this last one, in which the samples must be considered to be drawn from normally distributed populations or have sufficient size. And that's an or, not an and. That one is a little tougher with this limited bit of info because we don't have the raw data given to us. So here we will have to make an assumption about the individual values in the heart attack cholesterol sample. We'll assume that the 28 values from the heart attack, I'll call them group 1, from number 1 are approximately normally distributed. In this case, we need to make that assumption about that group number 1. However, the control group, the sample number 2, regardless of its shape, would meet the criteria for the central limit theorem. So even if we had the raw data, we would want to check if that raw data for the control group, group number 2, if it was normally distributed, but even if it was not, we would still be able to invoke the central limit theorem. So have we met these conditions? I think with reasonable assumptions, I think that we have. Another question worth posing here: if we had the raw data, how would we test for normality? That is by we might visually want to look at the QQ plots in R and then analytically check with the Shapiro test in R. In the Shapiro test, which is described in Lab 8, we would want the p-value to be large enough. In the next step, we will declare the null and alternative hypothesis, but first, let's identify the response variable. So what is measured? What is the variable to which we will discuss when we create our conclusion? What are these values measuring? They are measuring the cholesterol levels. So that is our response variable. For the null and alternative hypothesis, I'm going to state that the mean cholesterol level in the group that recently experienced a heart attack is the same as the mean cholesterol level as the group who did not recently experience a heart attack. Similarly, in the alternative hypothesis, we want to state that there is some sort of difference, but this video is all about a directional hypothesis. And we want to look at the description of the study to guide us in how we are constructing our alternative hypothesis. We will state that the mean cholesterol level is higher in the group that recently suffered a heart attack. I'm going to represent that with a greater than symbol. Next step, let's declare our level of significance, alpha. Were we told to use a particular alpha in the description of the problem? I don't think so. So what would we state as the default value for alpha? You got it, 0.05, right? And that corresponds with a confidence level of 95%, just as a reminder there. Next step, it's time to do some computations. If this was a lab assignment, we would have the raw data and we would ask R to do a T-dot test with a specific indication that we want an alternative hypothesis that is directional. But in this context, we're going to calculate this by hand. So I'm hoping that this test statistic looks familiar to you. And we identified group number 1 as the cholesterol levels from those who recently suffered a heart attack. The average there was 253.93. We're going to subtract the control group cholesterol levels, and in the denominator, we've got that big square root s squared over n for each sample. I've opened up R to use as a calculator, and I am double checking my input looks correct. Let's compute our test statistic. Wow, that's a 6 and change. That, I want you to think as a test statistic. Is that a big or a small test statistic? That is definitely big, because that's an indication that these two sample means differ by about 6 standard errors. If you recall about the empirical rule, 1 standard deviation from the mean, 2 standard deviations, 3 is pretty far. This is a 6 or so. And we're going to also calculate the p-value, but let me write this down in our notes. This is about a 6.146. I also want to draw a picture to help guide our p-value calculation. Because this was a right-tailed test, t-distribution, we need to also think about the degrees of freedom. We'll get there in a moment. This is a right-tailed test. I can see up here, this is pointing to the right. We need the area to the right of our test statistic. So I'm only going to shade to the right of this t-distribution. I am not shading both tails. Hopefully this picture helps guide our calculation of the p-value when we go to R. In this case, I am giving you the degrees of freedom of 37. So I'll write 37 right here in the image. As a reminder, this Welch-Satterthwaite method of calculating the degrees of freedom is not trivial, so I will give it to you. However, if I don't give it to you, if I fail you in that way, then we said just use the smaller of the two sample sizes as the degrees of freedom, right? You would do n minus 1 for whichever one of those is smaller. I'm not going to expect you to calculate that intense degrees of freedom formula that was demonstrated or shown in a previous video. Now let's go to R to determine this p-value. Because we want area or probability in the t-distribution, we want to use the pt function. Our t-value is 6.1457. I'm going to just type all of it because it's all right there. Our degrees of freedom was a 37. Now I'm going to do the wrong thing here, and I want you to tell me what is wrong with what I've entered. What is wrong with that? Well, look at this region. Isn't this a big test statistic? I didn't illustrate it to scale. Therefore, the probability in this right shaded tail here should be very small. But this is a very big probability. The error I have made, I have neglected to enter a 1 minus for that probability. So, our p-value, I do not need to double that. Remember what this does. This is going to move the decimal place 7 times to the left. Let's write that down. Let's see if I've written this correctly. 1, 2, 3, 4, 5, 6, 7. Doesn't really matter, right? That is a very, very small p-value. So we are ready for one of our last steps here, taking all of our information and stating a conclusion. Will we reject the null hypothesis or not? Since the p-value, gosh, it's small. It is going to be smaller than any reasonable choice for alpha. Remember, our alpha was 0.05. Since our p-value is less than alpha by a great deal, we are going to reject the null hypothesis. When the p-value is low, the null must go. I am also requesting that in a sentence or two, interpret this conclusion. Be sure to mention the study variables. So we're going to want to mention cholesterol level. We're going to want to mention what difference we have observed in our two groups. Let's get at it. So I would say something to the extent of the data provides sufficient evidence that the mean cholesterol level in recent heart attack victims, and that is compared to individuals who have not recently suffered from a heart attack. Let's highlight or emphasize certain aspects of this sentence. We are not proving that individuals who experienced a heart attack recently have higher cholesterol levels. We are not proving that. But the data provides evidence in support of that statement. We are inferring to a population parameter. That is what this mean is referring to. That is the population mean. The variable, study variables, we were looking at cholesterol level. And we were comparing cholesterol level in individuals who recently experienced a heart attack and those who did not recently experience a heart attack. Lastly, in our alternative hypothesis, we had a directional alternative hypothesis. So we want to state that directionality in our conclusion here. I have 2 more questions for you. Based on the limited amount of information that we were given about this study, does this demonstrate an experiment or an observational study? Remember the criteria that differentiates them. If this was an experiment, then we dictated, or the researchers dictated, who went into each group, right? They're controlling the explanatory variable. Did they assign the individuals to experience a heart attack? Of course not. They observed these cholesterol levels, and the individual subjects already existed in their respective groups. This is absolutely an example of an observational study. And do we know if an error was made in our conclusion? This is not a mathematical error that I am speaking of. Like, did we carry the 2? This is about a sampling error. The answer to this is we do not know. That's always the answer to this question when I pose it. We don't know if an error was made. However, if an error was committed, what type was it? Well, because we rejected the null hypothesis, this could be a possible type 1 error, but we don't know. It could have been a correct conclusion. Let's sum up this example. This has all the same elements of a 2-tailed t-test. The primary difference that occurs with a directional t-test is the way that the alternative hypothesis is structured, and then the way that p-value is then computed.